Good morning, everyone. I'm Guanjing Lin. I graduated from Texas A&M University and have been working here for 7 years. So in the past years, I have been working on different research projects about the building analytics. We've developed new algorithms, doing the demonstration, and also looking at the applications of these analytics technologies on the market. So today, what I will present here, it is a research project we have been launched 1 year ago. So the title is Development of Fault Auto-Correction Algorithms for HVAC Systems. So I'd like to acknowledge our team member here, Jessica Granderson is the project PI, and me, Guanjing Lin, and Marco Brittoni, and Yiming Chen. So what I will cover today is first I will give you an overview about this project background and motivation. Then I will present the fault auto-correction routines with 2 examples. I will also then talk about, since we have these research-grade algorithms, when we implement it in the real commercial tools and use it in the real buildings, what we need to be aware of. I will start the introduction of the fault detection and diagnostic tools. Anyone know what is that? Raise your hand. Okay, seems not many of you know what is this. So fault detection and diagnostic tools, it is a type of building analytics tools, which I showing the workflow here. That is, we see in a building HVAC system, we see the equipment like the air handling units here and the chillers, boilers, pumps, and then we know in the commercial building we have a control system which we call the building automation system. It sends out the control command to modulate the performance of this equipment. The FDD tool, it is built on top of the building control system. So this is a third-party software. So it reads the data from the building automation system. It reads the temperature, the pressure, the control signal, the schedule. It reads all these real-time time series, the operational data from the building automation system. Then what it will do? It will provide the visualization of all these data trends. And more important, it will perform the analytics on top of this data and then tell the operator, is there anything not right in the system? That means, is there any operation faults happen in the system? So the operators receive this message and then it can go back to the field to check what is really happened and fix the things. So this ensures the building system operate normally and also can improve its operation at some point. So the FDD research has been started, I think, about 40 years ago. And about 20 years ago, it started get into the market. And right now, we have seen dozens of full-featured FDD software products offered in the United States market. In the past 5 years, we've seen the increased use of the FDD tools in commercial buildings. So we launched a project called Smart Energy Analytics Campaign 3 years ago, which it is a project to document and encourage the building owners adopt this kind of analytics tools. So, and in that project, we collect the energy consumption information from these organizations, the energy consumption before they installed this FDD technology and the energy consumption after they installed this technology. So from the comparison of this energy performance before and after, we see the energy savings and the cost savings enabled by the FDD tools. So the two plots I'm showing at the bottom. The plot on the left, it is showing the 26 organizations' energy savings enabled by the FDD tool. So we can see it ranges from 0 to 30% with a median 8% energy savings. And then we multiplied the energy savings by a fixed utility rate. And the conclusion, it is the FDD tool enabled cost savings with a median of $0.27 per square feet. So this number, it is pretty encouraging. So we do see the FDD tool, it achieved the cost-effective savings in the field. So how these savings were achieved? That is another question we asked in the campaign projects. So when we send out the questionnaire, list the most common energy efficiency measures that building operators will take in the buildings, and asked them to tell us, okay, which of these measures have you been applied in your buildings through the use of FDD technology. And here I'm summarizing the top 10 efficiency measures have been applied. So no surprise, this result is pretty consistent with the energy efficiency measures we have seen from the commissioning study. So with the most popular one, schedule. So it is have a better weekly and weekend schedule and holiday schedule. And we also see this reduced simultaneous heating and cooling, that this can be realized by fixing the leaking valve, and also the improvements of other control set points, economizer, reset, and also improve the control hunting. So we are happy to see the increased usage of FDD in the commercial buildings. But at the same time, we do find that there are still opportunities we can advance these technologies. So if you remember the process I described for the FDD tool, it reads the data from the control system, it analyzes the data, provides recommendations. And the next, the operator needs to be there to see this information, digest the information, and then take actions. So we all know the building operators, they are super busy. So sometimes they cannot take actions immediately. And that is also one of the reasons when we see the FDD application, we see the largest portion user, it is the higher education, the universities, because they have this large facility, they have enough human resource to run the software and implement the efficiency measures. So we are wondering, okay, what if this fix can be done automatically? So you do not need to hire a contractor to do the fixing, but this efficiency measures can be done with your FDD tools. Once you identify faults, so you say, okay, it looks a real fault, I would like to fix it, and you click a button, boom. So you are already there. So this can make this open loop will rely on the human to fix the things to a closed loop to achieve the savings more quickly and more easy. And this is the motivation of this project. So we think this automated fault correction techniques, it can advance the performance of the current FDD technology. It will turn the one-way communication between the FDD tool and the building automation system to the two-way communication. So people, when they use the FDD tools, they can also have this way to automatically fix the things. So during the, so this is a 3-year project. Our study goals, first we would like to develop a library of the automated correction routines. And then we also working with our partners. We have 3 FDD providers, which they have their own commercial available FDD tools. So we are working with them to convert this auto-correction code into their development environment. And after that, start from this year, we will do in the field test. We will select the demonstration site and test our auto-correction routines in the real buildings. At the beginning of our study, when we thinking, okay, auto-correction of faults. So for the first things we need to figure out it is which faults are auto-correctable. So we know the FDD tool can report a lot of things. So I don't think 100% things can be fixed. So we are kind of looking through a big list and check one by one. Okay, is this fault can be possibly automatically correct? So I'm list some example here and want to do a quick exercise with you. So if you can take a look at this list for a minute, and I will invite some of you to answer the question and tell us which faults in this list do you think it is auto-correctable? Do you have a question?
Just one, overriding manual control. That seems like a simple one.
Okay, so you think override manual control, that is auto-correctable fault? Yeah. Any other opinion? Damper hunting. Okay, I see the second answer. So, yeah, go ahead. Zone temperature set point. Okay. What? The last one? Yeah, economizer lockout temperature set points. Yeah, schedule. So how about sensor reading errors? No. Temper control, honey. Okay. Okay, I think we can finish here. So let's talk it one by one. Yeah, most of you have already got the correct answer. Let's take those ones that is definitely not auto-correctable, like the damper stack, like the coil valve leakage. So we know these are the physical faults. So you cannot repair it without you have someone go to the equipment and replace the component of this equipment. So the ones that are clearly auto-correctable, I think are those related to the set points, because these set points, they are backnet accessible, so people is easy to overwrite the value of these set points. And some faults in the between, sensor reading errors. So I would say that depends. So if it is a sensor failure, the reading is 0, then of course we cannot auto-correct it. But it is a sensor bias. We see a consistent bias that appears in the sensor readings. Then we can find a way to add this bias into the measurements or have other approaches to overwrite the values. Another one, it is the damper control hunting. Yeah, this one is also depends if it is the hunting it is caused on an imperfect PID parameter setting. Then we can have a chance to correct the things. But if it is just because the capacity and other physical damage, then that is not correctable. So it is the ones in the between. So as I just talked about above, so the faults that require physical repairs or replacement, those we can only leave it to the building operator. But for the other faults that can have chance to automatically correct, we divided into two categories. The first category, we call this hard fault. This fault, we see the building operation, it is different from the designed operation. So that is, for example, our expect the HVAC system, it is turning on at 6 a.m. and turning off at 6 p.m. But when we see the building operation, and I find, okay, why the HVAC system is turning on at 4 a.m. in the morning? Then this is the difference between this and the design intent. We call it a hard fault. And a second category, we think it is opportunities. That means the operation, it meets the design intent, but we think that is not a super good operation. There are still opportunities to improve of that. Just for example, if you set the supply air temperature at fixed 55 degrees Fahrenheit, so I think that is not a good control strategy, and you can improve that to get more energy savings by implement the supply air temperature reset. So we have these two kind of category of faults that we can include it in our fault auto-correction framework. So after we find out which faults can be auto-correctable, in the past year, we have developed the fault correction routines for these 10 HVAC faults. The top 6, they are the hard faults, including the schedule, the override, the sensor bias, control hunting, the outside air damper position, and the rock zone. And the bottom 4, they are opportunities to improve different set points or set points reset. So this is the basic fault auto-correction process that we applied to all the 10 routines. So the first thing of this process, we are looking at the fault detection and the diagnostic algorithms to see if it is raised a flag that there is a fault. So after we confirm that there is a fault happening in the system, then we will initiate this auto-correction process. So we will find the correct control variables in the system and override these variables with a correct value. So when I say the control variables, what does that mean and what these control variables can be? I'm showing the closed control loop flowchart at the bottom. So for a typical control process, we will have set points, and then these set points will be compared with the feedback from the sensor. And then the difference between the two will be the input of the controller. And the controller decides the control signal that is sent to the control device. If it is a cooling coil, I will say this is the valve. And then the valve opening decides how many chilled water will be passed through the cooling coil. That is the process. So the things can be changed in this process. That is also the things I refer as control variables. They can be the set point. They can be the feedback from the sensors, or they can be the settings in the controller. So when we developed the auto-correction routine for a specific fault, we went through this process to find out, okay, which it is the best variable we will override. So I will give you two examples. The first example, it is the sensor bias. So how can we fix these problems in the system? We find out there can be two ways. The first way, it is we can override the temperature value. So here, the example here, it is a supply air temperature sensor bias. So we can override the supply air temperature value by adding or subtract the bias to its current reading. So how can we do that? In the control system, the settings, so the setting of the sensors, there will be a calibrate value in the sensors. So we can overwrite that calibrate values at this component. So when the sensor provides the feedback, it will automatically working into this bias value, and then it provides the correct value. Another approach, it is instead of overwrite the measurements, we are looking at what these measurements will be used for. So as we think, okay, what this supply air temperature will be used to control. So that is the supply air temperature set point. So instead of change the measurements itself, we change the set points to reflect the bias. A second example I'm giving here, it is the control hunting due to the improbable proportion gain that is setting in the controller. So this is a more complex process compared to the sensor bias. So we applied a trial and error procedure in this process because we do not know at the beginning what is the best value we should override to the system. So we will select a time the system is not in the operation, usually it's unoccupied time. Then we will start this system and adjust the proportion gain, the KP value, little by little. Every time we, for example, we reduce the value by 10%, and then we run a proactive test. For example, we set the damper position to 18%, and then observed with the existing FDD algorithm to see if the hunting behavior disappears. If it is not, then we keep adjust the KP value little by little until we see, okay, the hunting behavior is not there. Of course, in this process, we defined the maximum duration and also the minimum value as the ending criteria for this correction routine. So we will not want to run it endless. So we kind of set the bar. If it doesn't work after for how long, then we decide, okay, this cannot be fixed. So in the past year, we have developed these auto-correction routines. Now we are working with our commercial partners to implement these routines into their FDD tools. And we are start this conversation with them, okay, what things we need to be pay attention when we implement these auto-correction routines to their tools and real buildings. And here are the feedback we've got from our partners. The first very important feedback is we need to be very careful about the opinion from the building operators. So before we make any changes to the control system, we need to have the acceptance and approve from the building operator. For example, the override. So we observed override, we want to release the override, but at some time, maybe this is an on-purpose override for a short time test running by the building operator. So before we going forward for the auto-correction, we need to make sure the building operator understand the situation, and this is it, and then going forward. The second thing need to be aware of it is we are talking about overwriting the control variables, but for different systems, different building automation systems, the variable although they have the same meaning, but the actual data points may be different depending on the control system itself. For example, some buildings, the equipment schedule, it will located at the equipment controller. And for some other buildings, this schedule, it is located at a supervisory level. So we need to find the correct place to overwrite that value. And another example here, it is when you say the set point is override. Some control system, it is have a single data point. Say if the system is override, it is 1. If the system it is run automatically, it is 0. Then when we do the correction, what we need to change it is the value of this single point. But for the other buildings, what they will do is they may change the priority level of the command. So level 7, that has the highest priority, that is override, and level 8, it is showing the autocorrect. It is showing the normal operation. So what we need to change is the setting of this priority level. And also we need to figure out the things we want to override if it is backnet accessible. Because some of these parameters, they are not usually imposed, imposed to the third party to have access with. And there are also the things may need to be changed in the FDD tool itself. So one thing it is the current sample rate for the FDD tool, it is 5 minutes or 15 minutes. So if we want to looking at the control hunting fault, then this time interval, it is not sufficient for that. So the sample rate need to be increased to 1 minute interval during the fixing process. And also some FDD tools, when they say they are collect the real-time data, that is not actually real-time. They may collect the data once a day and then use the analytics to analyze the past day data. So some of our auto-correction routine that require the system to have these real-time assessments of the data. So what are the next steps? So right now, we are still working with our 3 partners to implement these routines into their tools. And start from this summer, we will test the algorithms in 1, 2, 3, 4 or 5 test buildings to see the effectiveness of the algorithms we developed. And that is the end of my presentation. And anyone have any question?
Yeah. My question is this, and I'm really intrigued by the idea of trying to do this stuff, but have you tried this at all over an MSTP protocol? Is the message traffic even possible over that slower protocol? Or is this only going to be able to be done when you have Ethernet connections between your nodes?
So this is done when during the discussion with our partners, one partner told us they will push it from the internet using the cloud structure because their analytics is located at the cloud level, and they will push the command from the cloud to the real buildings. And the other partners tell us they prefer to send the command just within the buildings. Yes, so there is no cloud level at this structure.
Right.
Yeah.
Yeah, I'd like to add to that. That is a real concern because we've implemented auto fault detection, but just the one way, not the auto correction yet. Using SkySpark software. And that was the concern from our end, from the facilities end, was the was the traffic. The amount of data. We found out that vendors typically want all data. And a lot of times we know they only need a fraction of that data. And so what happened, it clogs our network.
Oh, okay.
We found out when we trend points, we were having a hard time, grabbing that data on our end because the network traffic was so congested.
Yeah.
Along those lines,
Yes.
I'd like to add. So one thing we have to distinguish, and the Sky Foundry Sky Spark platform is fantastic. So what you guys are honing in on are some of the details of implementation and keeping the building controlled networks clean enough that they can do their primary function of control as you're adding this communications application, right? And so, yes, a poor implementation for FDD would be grab every data point that you think you might possibly need and grab it at 1 minute intervals. And then your network's going to bog down and you're going to have big problems. Now, I want to say that a clean implementation will recognize that certain points you only need out of all the points you have available to you. You don't need all 10,000 of them. You probably need 100 to run your analytics. You don't need them at a minute interval. Probably 5, and in many cases 15 on your power readings is going to do, right? And that all of a sudden makes a world of difference. That's all specific to the pre-existing FDD that's running, right? When it comes down to now pushing back the command for some corrective action, you've kind of already taken care of that. And now there is some nuance in some very particulars of these autocorrect routines, like how frequently do you need to keep pushing back? But with and this is part of the beauty of working with the implementation partners who already have a client base of thousands of buildings, is they're very aware of what is doable, and they will tell us quite quickly, oh, sounds good in theory, but we are not going to go do that. And so through the work, then, we've arrived at this kind of sweet spot of routines that we think truly are viable. And it really hasn't come up yet with someone saying, you know, my MSTP configuration is going to make this unviable, whether it's BACnet over IP or MSTP, what have you. So that is very much where our partners come into play and can keep us honest from the things we cook up here at the laboratory, what we can actually put into the field.
So for the auto-correction factor from the FDD, how is that integrated to the current BIS system?
So the auto-correction will be live in the FDD tools. So the FDD tools, when it identifies the faults, it will trigger this auto-correction routine. So the routine will send out the command from the FDD tools to the building control system and implement the changes intended.
Okay, we can take one more question. All right, thank you, Guanjing.